All right, so today we're going to talk about how to find the volume of a rotated object by using cylindrical shells. If you remember, we've done volumes before where we rotated an object, and what we used were discs or washers in order to find the volume after rotation. Well, this is just another method. It's called a cylindrical shell method. So what I want to do is I kind of want to remind you what it looked like and what the concept was for a disc and washer method, and then we're going to jump into what the shell is and why we would use the shell method. So we're going to take a look at a manipulative that's actually offered in your ebook here, but I want to show you what that looks like, and hopefully this will bring back some memories. Okay, so here we have just a very simple function, y equals the square root of x, and the bigger sketch of it is over here, and this is where we're going to actually show the rotation. So if we take this, y equals the square root of x, looks like we're just going from x equals 0 to x equals 1 here, and we rotate this around the x-axis. We can push the little animate button here, and we'll watch it rotate itself around the x-axis, like so. Perfect. And then what you can see is what they did was they put the disc here on the end. There's no holes in the middle of this thing, so it is a disc method. If we take this disc and we were to add up all of the discs from 0 to 1, you kind of go backwards. Remember that this is all the way back here at 0. It's a disc which is basically nothing. And then as we start adding up all the discs as we move to the right, each individual disc added together will give you the volume. Now, one thing I want to make sure that you guys see here is while we were adding up discs, and this is kind of some of the notational stuff that that we talked about probably very briefly last year. One thing you should see is come over here to this left side. Over here, that you can see that what they're using for your rectangle here is a midpoint rule. As you can see, the midpoint of the rectangle, the middle of this rectangle, is what's hitting up here on the curve. Now, the interesting thing is, this makes it look like this disc has thickness to it, and it does technically have thickness to it. But as we make this thickness, as we make this difference here in between these two vertical lines here, get infinitesimally small, the difference is just some kind of a very, very, very small change in x. That's where the dx comes from. That's what the dx stands for. It's the thickness of this. So when we added up all these things, what we were doing was we're taking areas of circles, pi r squared, but then we were multiplying those by the dx, which was the thickness of this. So technically, it was actually a cylinder. It was a solid cylinder. What we're going to see and what we're going to do today is we're actually going to have a shell of a cylinder, which is just the outside of the cylinder without the inside portion of it. And again, you'll see why. But again, notationally, I just wanted to make sure you guys remembered that when we did this, we were adding up all of the discs from one bound to the other. And by doing that, we were going to end up with the volume of this thing if it was rotated around. Oh, I didn't even know it could do this. There we go. That's really cool. Just found out something new, so I can actually rotate this and give you a different vantage point of what it looks like three-dimensionally. Well, that's really good to know. All right, learn something new. Okay, so now let's go back and let's look at this different method that we're talking about, which is called the shell method. Okay, so what you can see here is what we've got is we're going to examine the area bounded by the curves y equals 2x squared minus x cubed and y equals 0. So let's go ahead and just do a really quick sketch of what that looks like. Whoops. And if I didn't mention it before, I'll go ahead and mention it now. This is going to be a 2-video lesson. The first video, very much, and you guys should be used to this by now, very much is going to be just the setup, the why everything works, the how it works, just to make sure you have a really good background understanding. And then the other video is going to be our examples. And as you can see here, you will have 4 problems to work out. And this is from the ebook, which you may or may not have access to, but I will make copies of the problems for you and post them so that you have them. Okay, so now let's go ahead and, oh man. There we go. Let's look at this curve. Okay, if we were to sketch the curve, Let's do that in blue. From, I guess we're just going to start here. It's going to come up something like that, and then it's going to drop off pretty quickly like that. And y equals 0, of course, is the x-axis. So it's going to look something like that. The interesting thing about this is if we were to revolve this around the x-axis, this would be no problem. Okay, revolving this around the x-axis, and I'm not going to draw this on in there, but you could hopefully see that you would just end up using disks, and this would be really easy to do. The hardest part about the whole thing, of course, would be finding the radius, and in this case, the radius would be really easy of the disk. But if we were to take this thing and we're going to revolve it around the y-axis instead, well, that makes it a little bit more challenging because, remember, if we revolve this around the y-axis, and I will show you a much better manipulative of this, and you would have to find two radii, because you would technically have the radius that goes from here to here, and that would kind of be like your inner radius, and then you would also have the radius which goes from here all the way out to this side, and that would be your outer radius. But what you should notice is this is the same function no matter where I hit it. So the inside and the outside radius are going to be based upon exactly the same function. That makes it a little bit more challenging to do with a disk method. As a matter of fact, it's not going to work out easily for a disk method. One of the reasons for that is, in order to revolve this thing around the y-axis, we would have to solve this equation right here for x. That is algebraically very difficult to do. Okay, I'm not saying that it can't be done, but it is very difficult to solve that for x. So in this case, we need to come up with another method. So instead of me trying to draw this, let's go back to our manipulative, and we're going to take a look at what it looks like. So as you can see here, this is our equation, y equals 2x squared minus x cubed. It's drawn a little bit bigger up here. Now that I know this thing rotates, that's going to be kind of cool. We can take a look at what it looks like if I rotate from different vantage points. But let's go ahead and animate this. So this is going to be revolved around the y-axis. So it's going to start over here. It's going to revolve itself that way around the y-axis. I can't do it justice with the cursor. So let's just take a look at it. All right, as you can see, revolving that thing all the way around the y-axis kind of makes it look, I guess, like a little bundt cake or something. I don't know what you would want to call it. But what you can see here is now what we've got is we've got this this disc here, but it's not really a disc because there's a hole inside of it, and we have a pretty big thickness right here of the disc. So in this case, it really is a cylinder because this thickness is what's going to change as we go further out to the right. The thickness is going to get bigger or smaller depending on which way we go. So if I go more into the inside to the left, as you can see, the thickness is getting smaller, but what you can see is this really is a shell of a cylinder. What it really kind of looks like there to me is like a hockey puck with a hole taken out of it, and this one right here, but that's just me. If I move it more to the right, as you can see, the thickness as it follows the curve, and you're following the curve over here, as we go further and further up this way, as we start to get the maximum of this curve, the height of this thing, the height of this cylindrical shell gets really, really big. And as you can see over here, I'll show you in both of them, the height's getting big here, the height is also getting big here. The thickness of the shell is not changing. The thickness here is not going to be changing. That's going to be our D whatever. We'll get to all that when we develop this. And then as we go out further, the height gets bigger, and then the obviously the radius of this shell is going to change quite a bit. Okay, the radius is now pretty wide, and the further we go out to the right, the radius gets even more wide, obviously, and then the height starts to come back down. But again, one thing you should see is the thickness of this shell has not changed. The D whatever here of that shell has not changed. Now, if you really think about it, what that represents is the radius. So I guess we can talk about that real quick. It's the radius of the shell. The radius from here all the way out to here is really the radius. And there are two radii, which again we'll develop here in a second. But the two radii right here are really what's changing. So it's going to be some kind of a dr when we come to this, when we go to actually develop it. And if I were to take all of the shells that I can create from here all the way out to there and add up all those shells, it's going to give us the volume of this bundt cake or whatever this thing created. if I kind of back this off just a little bit so it's not fully there, I just want to take a look at it and show you from the top what that looks like. A little bit right there. And if we rotate it from the side, you can see, I'm turning it too much, but you can kind of see what happened there. Anyway, just to give you a different vantage point. If we put the shell back in, now I can show you from the top, it really does look like just a shell of a cylinder, a hollowed out cylinder. Anyway, so there's you go. There's the general idea behind what's happening. So we're going to add up all of these shells of these cylinders, and that's going to give us the volume of this thing revolved here. So once again, the main concept here is that the reason that we would want to do this is because we can't algebraically solve this for x very easily. This shell method can be used with other things as well. It can be used for anything that you just have a regular disk and everything for, as long as you can solve for the appropriate variable that you need to have. Because we're wrapping this thing around the y-axis, this one would have to be in terms of x. All right, so let's go ahead. First thing we really need to do is we really need to talk about the concept of the shell. I'm not sure what happened to my picture there. Kind of got cut off. That's weird. Do I have the one on the bottom? Okay, I've got the one on the bottom. Huh, that's weird. Anyway, don't really need to have the whole shell there, but okay, so let's talk about the cylinder, and specifically the cylindrical shell. So the first thing that we need is, in order to be able to find this, we need to know how to find the volume of a cylinder. And hopefully remember that the volume of a cylinder is pi r squared times the height. Or basically, a circle or a disk, pi r squared, times a height. A whole bunch of disks stacked upon themselves gives you the height. So the volume of a shell, oops, accidentally erased that a little bit. Volume of a shell would basically be the volume of the outer part of the cylinder minus the volume of the inner part, the part that's taken out, the part that's been hollowed out of this thing. And that's the general concept there behind what we're doing. So let's go ahead and take a look at this drawing real quick. And there is one piece, there is one piece that's missing from the right-hand side here, so I'll just kind of draw it in when we get to it. But what you can see is, let's go with blue, I guess. We do have an outer radius, R2, which goes all the way to the outside of this thing. Then we have an inner radius, R1, which hits the inside of this thing. And what the part that got cut off here is that the thickness of this part right here, the difference in between, oops, let's go with that color. The thickness in green, that's your delta R. Okay, that's the change of R. Because you do have an outside radius and an inside radius, so there is going to be somewhat of a change in R. And as we start to let that thickness get really, 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 really small, that's when it will become the dr part. And again, we'll get to that. And then, of course, with a cylinder, we also have a height. Well, that's just how tall the cylinder is. So that's from the top of the cylinder all the way down to the bottom. Okay, so let's go ahead and develop how we're actually going to be able to find this thing. So the first thing is we're going to start off with, if we have a cylindrical shell, the volume of the entire shell is going to be pi times the outside radius, which is R2, squared, times the height. That's going to give you the volume of the entire thing as if it was a solid cylinder, no hole taken out of it. But we want to take the hole out of it, so that's going to be subtracting pi times the inner radius, which is R1, squared, times the height. Okay, and what you should see is I have a pi and an h in common, so I'm going to go ahead and factor out the pi and the h. I'll do pi and then h on the outside here, and all I have left over is R2 squared minus R1 squared. All right, so now what we can do is, and you wouldn't normally probably think to do this, but what we can do is I can go ahead and multiply I can go ahead and multiply a 2 on the right-hand side. So I'm going to make that a 2 pi, and then I've got my R2 squared minus R1 squared times h. And you might think to yourself, wait a minute, you can't just multiply the right-hand side without multiplying the left-hand side. You're actually correct, unless I divide by 2 as well. So now I'm not just multiplying by 2, I'm also dividing by 2. So I'm really just multiplying the right side by a factor of 1, just a weird way of doing it. And again, I'll show you why we're going to do that in just a second here. This R2 squared minus R1 squared is the difference of squares, so that can factor. So we're going to get the volume here to be 2 pi, and then it'll be R2 minus R1, R2 plus R1, h, and I have to divide it somewhere by 2, so I'm actually going to put the divided by 2 underneath the R2 plus R1. It didn't really matter where I put it, but I am putting it there for a specific reason. Okay, so what is R2 minus R1? What is this part right here? Well, that's just delta R. That is the change of R. That's R2 minus R1. So that's what delta R is. R2 plus R1 over 2. Well, if you add two things up and you divide it by 2, it's really just the average. It's the average radius. So in this case, the average radius is just what we're going to call R. It's the midpoint, in other words. So this piece right here, let's try this color. If we go with orange, this piece right here, that's just the midpoint. And as we saw from the manipulative, the midpoint gives us our radius, because as we make these infinitesimally small, that just becomes R. So really what I have for my volume after all of that is we have that the volume is 2 pi. This part in orange was R. The part where the R2 minus R1 was delta R. And don't forget we have a height. So we have height delta R. 2 pi R h delta R. Well, if you think about it, 2 pi R, this is something which should be familiar to us. 2 pi R is just the circumference of a circle. Circumference. I think I spelled that right. The h part, okay, that's the 2 pi R. The h part, well, that's just the height. And then the delta R is your thickness. So when you want to find the volume of these cylindrical shells, it is the circumference of the shell times the height times the thickness. 2 pi r h delta R. And what we're going to have to be able to do is figure out what R and H and delta R are, because 2 pi is just the constant. So that's what we're going to talk about next. Okay, if we scroll down here to the bottom of the page, this figure right here is what we're actually going to look at on the next page. We're just going to break it down into smaller components to make it a little bit easier to see what we're doing. But what we've done is we've taken some function, and again, it got cut off here. That's really weird. That's going to be some function f of x. That this is the function right here. I'm trying to trace it the best I can. Right there, that's our function. What we did was we revolved it around the y-axis. And then what we're going to do is we're going to try and find the volume of this thing by using the cylindrical shell method. So let's take a look at the next page. And what we did was we broke this thing up into shells. So what you can see is, once again, here was your function, y equals f of x. It's really weird that the drawings got cut off, but the words did not. So here's y equals f of x once again. And what we did is, once again, you can see that each one of these, the thicknesses here of these shells is split up to the point where this right here was the midpoint, that's the midpoint, that's the midpoint, That's the midpoint. All of these shells right here have a thickness where the thickness is hitting the midpoint of the rectangle there. And the biggest thing is that on each one of these, the radius, because that is going to be important, the radius goes from the center of the axis of revolution out to the middle. The center of the axis of revolution out to the middle. The center of the axis of revolution out to the middle. Well, every time, that is some kind of an x value. So in this case, because we were revolving this around the y-axis, the radius is just x. It's some x value. And it's going to change, which is why it has to be a variable. It's x. It's always going to be an x value when it goes out from the y-axis out to the function. Obviously, that can change if this is revolved around something other than the y-axis, and we will get to an example where that happens. So the general idea is here, if we want to find the formula for this, remember, it is the circumference of a circle. Well, the circumference is 2 pi r, but in this case, r is x. So the circumference is going to be, in this case, 2 pi x. The height of this thing, the height of each one of these pieces is the function itself. Okay, the height goes from here up to the function, goes from here up to the function, goes from here up to the function. All of those in green are the height of the function. Well, that's just f of x. F of x, in this case, defines the height of the function. And then, because we do have a thickness of this thing, the delta r, well, r is the same as x in this case, so really, this is dx. And then if I want to take and I want to add up every single possible shell, I integrate. So we will integrate from a to b of 2 pi x f of x dx. That will give us the volume. Okay, and to kind of help, and I know this video is running a little bit long, be about 25 minutes, I think, when we're done. Just to help a little bit more, another way to visualize a cylindrical shell, just so you get the idea of why it's 2 pi x, why it's the circumference, is because if we were to take and slice this shell, if I were literally just to take some kind of a, I don't know, some kind of a knife or something and just slice it right there and open it up, it looks like this right here. Okay, it just basically looks like a rectangular prism. It's got a very, very small thickness to it, but it is a rectangular prism. Where if I were to go all the way around the outside of this thing right here, that's the circumference, that's the 2 pi r, in this case 2 pi x, because the r is x. So there is the length of your rectangular prism. The rectangular prism has a height to it. Well, that in this case is f of x. But that right here, the height is f of x. And then it does have a thickness to it, which in this case is just some kind of a change of x. So this piece right here has a thickness, which is your delta x. If you make that infinitesimally small, it becomes dx. So really, all you're really doing when you find the shell is you're adding up or finding rectangular prism volumes. That's all that it is. So once again, you would take the integral from a to b of 2 pi x, that's your circumference, times the height, which is going to be your function, times the thickness, which in this case is dx. All right, so we're going to come back now and we're going to do a few examples. I think I've got on here, I've actually forgotten how many examples I have. I've got four examples, and that should be it.